So today's lecture is about a concept which you are familiar with. It's the scalar product, but we're gonna make it an abstract. You know this concept in terms of geometric vectors, but we're gonna make it an abstract concept applicable to all kinds of vector spaces. So scalar product is also given another name, which is inner product. So let's first recall what scalar product is on the geometrical vectors which you are familiar with. So if you have two vectors, let's say V and W, then we define the scalar product which we write with a dot. So you can call it scalar product, dot product, or inner product. They are all the different names for the same concept. So as you can recall that the dot product is simply you take the length of the first vector. So when I write these two bars, that means I'm considering the length of this geometrical vector, multiply it with the length of the second, and then take the cosine theta, cosine of the smaller angle between them. So if they were like this, I would take this angle, theta, and not this angle. Or if they were like this, I wouldn't go this way. I will take this smaller angle. So this is then an unambiguous way of assigning a number starting from two vectors. So you're given two vectors v and w, which I have drawn over here, and the scalar product gives you a number. Depending on what kind of vectors you have, what is their length and what is their mutual angle. So this should be thought of as an operation that assigns numbers to a pair of vectors. So in other words, scalar product is a machine that takes two vectors and spits out a number. So you can write it this way. This is also a notation which is very commonly used when you are talking about scalar product in general. So you have this kind of machine and it has two places. You give it two vectors and it produces for you a number. Now for these geometric vectors, the scalar product which you are familiar with, it has certain properties. So what are the properties? First of all, if I write this or I write this, first write the W and then write the V. Doesn't matter because the formula in this case would be write the length of W first and then write the length of the V and then cosine theta. But it doesn't matter, these are just numbers being multiplied. So V dot W is equal to W dot V for scalar products. So you can say it's commutative. And also, I can give in this operation over here, I can give two same vectors. So taking the scalar product of V with itself, the two vectors you have to give, you can give same vectors. So scalar product of V with itself is V's length times V's length and the angle between the two V's. And since the V's are same, the angle is 0. So cosine of 0 is 1. So you just get the square of the length. The scalar part of a vector with itself is just the square of the length. And the important thing to note is this is not 0, and actually it's a square, so it's greater than or equal to 0. Because it's a square, so it's a positive number. And it's equal to 0 if and only if the length of this vector is 0, but that vector is the 0 vector. Only the 0 vector has length 0. So if I take the scalar product of a vector with itself, I'll get a number which will be positive. And it will be 0 only if the vector itself is 0. And I will never get a negative number. So that's the second property. And then you also you have studied it, that you can prove that if I take two vectors, add them to get a third vector, and take the scalar product with the W with another vector, then this splits. We are familiar with this property of scalar product of geometric vectors. It splits. And also if I have something like this, this is equal to taking the scalar product and multiplying that with a number. So combinedly, I can write it like this. This is, you can call the linearity of the scalar product or a distributive law. So this splits. Plus B times and since the scalar product, you can change the order. First write the W and write the and then write the V's. So it works. It doesn't matter if I have a sum in the second vector. So I will also have this property. V1 dot W1 times A is B V1 dot W2. So in general, this thing breaks up. Dot, this is completely general. They're just gonna break up in the obvious way. Plus AD V1 dot W2 plus BC V2 dot W1 plus BD V2 dot W2. So this is the linearity of the scalar product. Now these properties which you have learned in your high school, we're gonna generalize it to an arbitrary uh, vector space. So when we do that, we usually call it an inner product. So now I'm gonna define the inner product or scalar product on an arbitrary vector space by abstractly assuming these properties for an operation. Inner product on a vector space. We got the idea of this scalar product to something which we know about the geometric vectors, but now we're gonna generalize it to any vector space. So I say that on a vector space V, doesn't have to be these geometric vectors, any vector space V, an operation which takes two vectors and gives a number is called inner product if these properties holds. So what are the properties? I just generalize all those things which I had written above. So first of all, I demand that this operation, sometimes people call it form, operation, a function, a bilinear function on the vector space, because it gives you, takes two vectors and gives you a number. But let's just think of it as an operation or a machine. It's a machine which is defined for every pair of vectors. V, an operation which takes two vectors and gives you a number. So it has these properties that if you flip the order, you still get the same number. So as soon as I write this bracket around these vectors, I know that I have converted these vectors into a number. This guy now is a number, same as this guy. And the first property demand is that the number is same no matter which order I put it in this machine. Then the second is that if I give this machine the same vector in both places, so it's like making the scalar product of the same of a vector with itself, then I'm just generalizing what I found over there, then it should be a positive number equal or greater than 0, and it should be 0 equal to 0 if and only if V itself is the 0 vector of the vector space, not otherwise. Finally, you want the linearity, alpha V1 plus beta V2. This splits V2 W. Now you just have to write it on the left hand side, and now you know that this linearity will hold on the second argument as well, because it's symmetric. This thing is also called that the scalar product is symmetric. just a name. So this automatically implies 3 and 1 imply, you don't have to assume it, that if I consider it in the second argument, a linear combination in the second argument, this is equal to by 1, the first property, that is symmetric. And this is equal to by 3, that is linear in the first argument. But now I can flip again. So I have proved that this linearity holds in the second argument as well. So we can break up the scalar product. This is what I have written is just the is just not generalization, it's just taking those properties and then defining the same kind of object on any arbitrary vector space. This symbol for scalar product of two vectors, you can write it this way as well, as with a dot. There's no difference. Many people write it with a dot. The book, when it deals with a general vector, not only a geometric vector, it prefers to write it with this triangular bracket. So I'm just sticking to that notation. Now, what are the examples? So if I consider Rn, vectors in Rn, so suppose you have V and W from Rn, then I define the scalar product as, make this the first one as a row and multiply it with the column of W. So what would it be? These are the components in the first vector, which I have made at a row by taking a transpose. And the second one has these components. So when I take this matrix product, I get just a sum of product of corresponding components. We have seen it before as well. That's just the scalar product. Sum of product of corresponding components. Now we have to check, why is this really a scalar product? It's defined for any set of vectors. First you have to make sure that it is defined for any set of vectors. Well, obviously it is. It gives you a number. This is just a one number. And we have to check those properties. Since VW is simply, we have to make sure that this is true. But if I write WV is simply, by the definition of this product, is simply this thing, which is obviously equal to, these are just numbers, so I can flip the order. This is just same as VW. So the first thing holds. Number two, you can, by the way, you could have seen it through this as well. Since it's a number, if I take the transpose of a number, that's the number itself. So this is equal to transpose because it's just one single number. But now if I use the property of transpose, then I know that I have to reverse the order. And transpose of a transpose is the thing it's back itself. So this is just some cute technique using transpose. Now, what about this second property? We want VV to be positive definite. It has to be greater than 0. This is just V1 times V1 plus V2 times V2 plus Vn times Vn. So V1 square plus V2 square plus Vn square. So it's a sum of all positive numbers. So this has to be greater than or equal to 0. And it will be 0 if and only if each one of them, because none of them is negative, if each one of them is equal to 0. But that just means that I am dealing with this vector, which is the 0 vector of Rn. Now the third property obviously holds as well, because if I take A V1 plus B V2, this thing. So what is this? The first vector has components AV1 plus B. Well, this will be a bad notation. Let me use, because I'm using V1 for the components. Let me write V and U. So what's the formula for the scalar product in this case, which I have defined? This is how I have defined the scalar product. You have to give a rule. You define it yourself. You have to come up with some rule which has these properties, three properties. Actually, we will see that you can have many different rules. You can come up with any rule as long as it satisfies these three properties, then it will be one scalar product on the vector space. And you can actually put many different scalar products on the same vector space. But the rule which we have chosen, if I apply this, so the first vector is the sum of AV plus BU. So it has components AV1 plus BU1. I have to multiply it with W1 plus AV2 plus BU2, W2, until I have AVN plus BUN, WN. But now I can split open these products. These are just some numbers. And I will have W1 plus B U1 W1 UN WN. So this is just A times V scalar part of V with W. And this is just B times scalar product of U with W. So the third property holds as well. That means the formula I have written, it is indeed a scalar product. Now let me give you another example. I consider the space of, well, actually I can consider M by N matrices. I know that this forms a vector space and I want to give a scalar product on it. So I give the scalar product with this formula. A and B are matrices, M by N matrices. So I give it by trace of A transpose times B. So what is trace? We did it in a homework, but let me just remind again, just give the definition over here. First of all, notice that I can really multiply A transpose with B because A is M by N and B is also M by N. So I cannot multiply A with B, but if I do A transpose, that is N by M. It has N rows and M columns. This I can multiply with B because its columns match with this rows. And it will give me an N by N matrix as some answer. So what's the trace? You take whatever matrix you have. This is an N by N matrix. So you just sum over its diagonal components like this from 1 to N. But I can write this product. So it's the ith component of this product. How do I write it? I have to introduce another index j, which I sum over. So ith component of A transpose times B would be this with a sum over j from 1 to M. But this I can write is a transpose. If I take the transpose, it's just AJI and BJI. So all it's saying is take the components of the two matrices and take each component, multiply them, and sum over all these kind of multiplications. So now let's see if this is a scalar product. So the first property I have to check is AB equal to BA. Now if I write BA is just a B Ji A Ji, and this is just equal to, these are just numbers, so I can write it as Bj. What is Bji? Is jth ith component of B. What is Aji? Jth ith component of A. These are just numbers which are being multiplied, so I can write it like this. But this is the definition of AB. So BA is equal to AB For the second property, I want to check what is this. So according to this formula, this is just Aij. I goes from 1 to m, j goes from 1 to n. Because the first component goes from 1 to n, m, and the second component goes from 1 to n. It's a m by n matrix. UI did AJI or AIJ, doesn't matter. These are just indices which are being summed. You just have to remember that the first index is being summed from 1 to m and the second from 1 to n. Aij times Aij, because it's the same matrix which is being multiplied twice. So this is just Aij squared. You're summing over some positive numbers. So it's going to give you something, some number which is positive. And this will be 0 if and only if all Aij's are 0. But that means you have the 0 matrix, which is the 0 vector of this space of m by m matrices as we wanted. And number 3, you can also show is just simply the matrix algebra that is beta b times c does split up because matrix multiplication is distributive. So this also happens. So the formula I have given you is a scalar product. Let me give you an example from the space of polynomials. For Pn, which is, I'm using the book's uh, uh, terminology, Pn is are the all the polynomials of degree up to n minus 1, right? So these are these kind of guys. Where these A's are just numbers. So all these kinds of objects, if you collect them, it's a n-dimensional vector space. And I say that to define a scalar product, consider n distinct numbers. Let's call them y1, y2, up to yn. And using these, it's up to you. You can pick any one, and each set will give you one scalar product. Using these, define the scalar product between two polynomials px and qx as summation I1 to n. You just replace the value of the polynomial when you put x equals to this number. So you evaluate the polynomial at the value at this number, x is equal to this number. So you do it for the first and the second, multiply them, and sum over all these n numbers which you have collected. Now it's obvious that the first property does hold. It's just the same thing. I don't need to even write. This is true. Now you have to check if this is true. When you do this, you get p square of yi, and this is going to be greater than or equal to 0 because these are all positive numbers. And this will be equal to 0 if and only if this p evaluated at yi is equal to 0 for all yi. You have collected n yi's, and for each value of p over there, it should be 0. But this is impossible. Impossible unless p of x is 0 polynomial. Because what is this equation saying? This is saying that you have this polynomial of degree n equal to 0 and you are finding its solutions. Some numbers for which this becomes equal to 0 of this equation. This is this equation. I have opened it up. So some yi's satisfy it. But we know that if you have a polynomial of degree n minus 1, then it can have at maximum n minus 1 roots. So if I have collected uh, n numbers, then no matter what polynomial I think of, I can choose any a's I like. I can test with different a's. It's never going to satisfy this equation unless this polynomial is identically 0. Because a polynomial of degree n minus 1 cannot have n minus 1 root. Like if you have a quadratic equation, it has only two solutions. At maximum, it can have only two real roots. If you have a cubic equation, it can have at most 3 roots. So if I am having third degree polynomials, but over here I said if it's P3, I'm going to collect 4 numbers. If it's P4, I'm going to collect 4 numbers. So that means I have polynomials up to degree 3, but I select 4 numbers. So these 4 numbers there will be no polynomial which is 0 for all these 4 numbers because it's not going to have 4 roots. So only this possibility is true. So because of this, I'm saved and I do get this, that the scalar part of a polynomial with itself is 0 if and only if p of x is the 0 of the vector space. Because the 0 polynomial is the 0 of this vector space. And the last property is also obvious, so you can prove it yourself. I'm not going to do it now. So this concept, let me just introduce a term. So we borrow, since we have distilled all these properties, all these definitions which go into all these properties which go into the definition of the scalar product from our geometrical vectors. So we borrow our intuition, which we can only borrow it, but we have to check. We have to make sure that whatever our intuition is telling us can actually be proved using these three properties. So we borrow our intuition and terminology from geometrical vectors. So, for example, we know that in geometry, if two vectors have a 90-degree angle between them, then the terminology used is that they are orthogonal, that they have a 90-degree angle. People call it orthogonal or normal to each other. But then the scalar product is, using the formula for the scalar product of geometric vectors, is 0. So I'm just going to borrow it and define orthogonality. It's just given a name to a special, if you get this number, that if the scalar product between two different vectors is equal to 0, then we say V and W are mutually, it's not their own property, it's a property relative to each other, are mutually orthogonal. They are orthogonal to each other. They may not be orthogonal to other vectors. So it's kind of, there's a 90-degree angle between them. Although these objects could be some very different beasts. Now, this, let's check this thing. That if I consider R3 or R2 and I write I know that if I have a vector in R3 defined this way, I can map it to this vector. I can make a geometric vector in R3 using this. So it has some component along x-axis, some component along y-axis, if it's in 2-dimension, and if it's in 3-dimension, it has some component along z-axis, which are v1, v2, v3. Now, I know that if I take one vector v, another vector w, then I can write the difference of them, which would just be this vector by head to tail rule, because for the geometric vectors, the sum is defined using head to tail rule. So this has to be w minus v, so that when I add these two, I do get w back. So this guy has to be w minus v. And this angle is theta. Now, if I form w, well, first of all, yeah, w minus v length. What would be length? I think I have, yeah, I discussed it. Yeah, did I discuss it above? Let me just discuss it again. I think I did. If you take the scalar product of a vector, geometric vector with itself, it's this. So it's v square, length square. That means the scalar product of a two geometric vectors of a geometric vector itself is just the length square. So I can take this W minus V and compute its scalar product with itself. This I know is going to be the length of this vector squared. But over here, I just use the distributive law, the linearity, minus W dot V. Now you can notice because these are geometric vectors, so I am just for clarity using the dot symbol for the scalar product. I'm just opening this over here. Minus V dot W plus V dot V. So this is W dot W, which is W length square, like over here. And since they are V dot W is same as W dot V, so I can write it as 2V dot W plus V's length square plus V's length squared. And this is just V length, W length times cosine of the angle between V and W. That means I can bring this to this side. So I have 2VW cosine theta plus V square minus V minus V square and then this thing, I bring the half on this side. This thing is just V dot W. That's the very definition of V dot W. V's length, W's length, and cosine theta. So what is it telling me? What it's equal to? If now I consider these V as these column vectors, then what would it be? It would be W1 square plus W2 square plus W3 square plus W minus V, V1 square plus V2 square plus V3 square minus W1 minus V1 square plus W2 minus V2 square Wn minus Vn square. I'm only considering up to 3. So when I open this up, I get W1 square plus V1 square and terms like 2V1 W1 and so on. So these cancel with these and all these terms. And I'm left with this 2 cancels with this half, and I have a minus times a minus. So I just get V1 W1 plus V2 W2 plus V3 W3. So this shows that the scalar product which I have defined, this one, that V transpose W, is same as this geometric scalar product. If I translate these vectors as the components in the 3 space. So the scalar product which I have defined as the sum of the product of components is same as this. So if I have to compute the angle between two vectors in three-dimensional space, I can just use this formula to compute the scalar product between them, and then use the similar formula to compute V mod, which would be V1 square plus V2 square plus V3 square root. W mod would be W1 square plus W2 square plus W3 square. And then just do this. And this would be cosine theta. The angle, cosine of the angle between them. So like if I'm given this vector, 1, 2, 3, 3, 1, minus 2, I compute the scalar product, which is 1 times 3 plus 2 times 1 minus 3 times 2. So I get 3 plus 2, 5 minus 6 minus 1. And V's length is 1 square plus 2 square plus 3 square under root. So it's 9 plus 5 under root 14. W's length is 3 square plus 1 square plus minus 2 square. So this is also under root 14. And the cosine of the angle between them is minus 1 over 14. Because minus 1 times under root 14 times under root 14 is minus 1 over 14. So you can, on your calculator, you can compute whatever this number is. So this idea, then you generalize it to any vectors. You say that if you have any two vectors in any space, maybe Rn or polynomials of some degree or matrices, and we will see some other examples very soon as well. You just take these elements, two vectors from there. This thing you will call this object. If you compute this, this would be cosine of angle between them. Right now, we don't know if this is really a cosine, because I don't know if I'll do this. Will I get a number between minus 1 and 1? Because cosine is only between minus 1 and 1. So this I have to show that if I define an angle between two vectors like this will happen. But I can at least define the length or norm length or norm of any vector, it would be simply v dot v under root. And I can take the square root because it's going to be v dot v is already a positive number. Now let's use some intuition to derive some possible theorems about scalar products in general. So this, let's call it theorem. Yeah. Pythagorean law. So if I consider geometric vectors, v and w, I know that how to add them. I put this w over here. This is w now, and this is v plus w. So I know by Pythagoras theorem, if this is 90 degrees, if it's a right angle, which means if v dot w is 0, if v and w are orthogonal, then if v dot w is 0, then the length of the hypotenuse, so in terms of vectors, it's just this, its square is equal to square plus w square. Now, in general, what would it say? Let me just use the terminology, the notation for any, this is a guess from this geometric intuition. For any vectors, and let's see if it turns out to be true, v and w belonging to any vector space v that are orthogonal. What is our definition of orthogonal? That their inner product is 0. We will have v plus w length is equal to v length square plus w length square. And what do I mean by length? These are some abstract vectors. There's no other meaning to length except that v plus w mod square is actually just the scalar part of this vector with itself. My vector is, what is my vector? V plus w. Its scalar product with itself gives me the length square. That's just a name for it. It's just the length because I have borrowed the terminology. Now, all I have to do is use the linearity that this splits up plus w. Now, this is just, the terminology is that this is just this v square, and I assume that they are orthogonal. So this is 0, and this is 0. So, and the last one is just the length square of the w. So it's almost like a definition. So this is true. This geometric intuition from geometric vectors holds up in any vector space. Let's take an example. Should I do the theorem or should I do the example? I think let me just first do the next theorem. Now, so this was the Pythagorean theorem. Now let me borrow some more terminology. Projection of a vector onto some other vector. So I can talk about two things. Scalar projection. What is this? So if I have a vector v and another vector w, so I just project it over here, that what is the component of w along v. This is well defined in geometry. So what it would be, you know, it would be just the length of w times cosine theta. So this is the component of w along v. Scalar projection of w onto v. What is it? It's just the component of w along v. And it is just times cosine of theta. But this I can write as a scalar product, because if I introduce the length of v over here, so if I have multiplied it upside, I can divide it downstairs to go from here to here. But then the upside now just becomes v times w. And I have this over here. So this would be, but now this is all written in terms of inner products. This is v times w over v times v square root. So this is just vw over v square root. So that would be, so this thing I can now call it, because this is now written only in terms of vectors and inner products, which these things are defined for arbitrary vector space, even if there is no concept of cosine theta, because right now I don't know if cosine thetas exist or not. I don't know if this scalar product between two vectors always leads to something like cosine theta. But this is well defined. So this I will call, in general, projection of W along V. This was scalar projection. Now I can take this length, which is this number, and multiply it with a unit vector in this direction. That will give me a vector which is equal to the projection, whose length is equal to this projection and is directed along V. So this would be called the the vector projection of W along V. So what I need to do to get this, I had this as my required number, and I make it a vector by giving it a direction. What is the direction of V? But V is a full vector with some length, So I divide it by its length to get a unit vector of unit length over here. So this will then become, the formula will then become V mod square V. And in abstract notation, this is just this. And this thing is now defined for any kind of vector. So this will then become vector projection of W along V in any vector space. So you can play this game and you can prove a very useful theorem. So what's the another theorem you can guess using your geometric intuition? So what's the intuition? So again, if I get two vectors and make the scalar product between them, U and V, I know in geometry the formula is this. This is the scalar product. And cosine, since cosine theta is at maximum equal to 1 and otherwise it's less than 1, so I know that this is going to be less than or equal to UV. But there is a problem that cosine theta can become negative, right? So I can improve this. So if they are like this, so I will have some negative term over here, but this side is positive. So I can improve this thing by considering the positive number over here, because I know that it will still be greater than, it will still be less than, if I make this negative number, change it to positive number, it will still be less than this, because the positive number will be less than 1. So I can say, I make the positive number out of the scalar product. Scalar product can be positive or negative, depending on if the angle theta is less than 90 or more than 90. So I make it positive, and I know that this is still going to be less than the product of the length of the two vectors. So it's a bit stronger statement from where you started from. This thing is called the Schwarz inequality. And we want to show, here we guessed it, it's true for the geometric vectors. We want to prove it for any vector, any abstract vector. So how do you show it? Let's suppose I think the proof, maybe we should leave the proof because we are nearing the end for the next time. Let me just make a comment. If this were true, let's write it as a theorem, which we will prove next time. For any vectors V and U in a vector space, u dot v mod is less than or equal to u dot v with equality holding only if u is a multiple of v, or the same thing you can say, because these are only two vectors are involved, u is equal to some scalar multiplied with v. So they are, if u and v are linearly dependent. That's what you mean. If there's a if u is v is a multiple of u, or u is a multiple of v, that means they're linearly dependent. Now, since this is true, and this is called Schwarz inequality. I could have probably written it like this in the more abstract notation. That's the Schwarz inequality. And if this inequality is true, which we're going to prove next time, then from this inequality, you get, by dividing by u length and v length, it's less than or equal to 1. So the modulus is less than or equal to 1. So the number itself, this number itself, I do not do anything to these positive numbers which are downstairs. They stay like this. But if I remove this mod, that would mean that I get a positive number or a negative number. So that's the Schwarz inequality, another form for Schwarz inequality. That if I take the scalar product of two vectors, divide by the lengths of those vectors, I get something between -1 and +1. That means this number, which is between +1 and -1, I can represent it with the cosine theta, because cosine theta's range is between +1 and -1. So then I can use this to define an angle between two abstract vectors. And you can see that defined this way, if u and v are orthogonal, it's 0, which we called orthogonal, implies the angle is 90 degrees. But it's just a name given to this object, and it's very helpful in intuitively thinking about these abstract vectors. That there's an angle between them. Are they collinear? If they are collinear, if you find the angle and it turns out that the angle is 0, that means they are collinear. That means they must be linearly dependent. Or if they are orthogonal, then they have some other properties which can be very useful. So we will see further details of this theorem and its applications next time, and many, many more examples. Any question? Is there a question? If not, I'm gonna end it here.